In this video, we are going to talk about the derivative of a function. So recall from the last video that the derivative of a function at a number a is defined to be f prime of a equals the limit as h goes to 0 of f of a plus h minus f of a divided by h. And we're going to use this definition and just kind of expand it to define the derivative of a function. So given any number x for which the limit of f prime of x exists, we define the function f prime to have value f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x divided by h at point x. The function f prime is called the derivative of f. Now, this is kind of a subtle thing. Basically, all we're saying here is that instead of just looking at a single point, now we're looking at all possible points where this limit exists, and we're just making a function out of it. So we're just defining some function f prime whose value is this limit for any choice of x where this limit exists. Now the domain of f prime is the set of all x such that f prime of x exists. And this may be smaller than the domain of f. So when we take the derivative of a function, we may get a smaller domain. We're never going to get a larger domain because f of x has to exist for this limit to exist, but you may get a smaller domain from doing this. So let's look at some examples of actually computing this function. So given f of x equals x cubed minus x, we want to find f prime of x. And so for this is just saying we want to find f prime of x, which is the limit as h goes to 0 of f of x plus h minus f of x divided by h. Now the only difference between this and what we were doing before is that now in our limits we're going to have a number x in the place of an actual number. So we're working with a lot more symbolic manipulation here than what we were doing before, but it is a limit similar to what we've done before. So this is the limit as h goes to 0. F of x plus h would be x plus h cubed minus x plus h. And then we minus off f of x, which is x cubed plus, minus x. And then divide that all by h. So we're going to multiply the top out. So we have the limit as h goes to 0. Multiplying the top out, we get x cubed plus 3x squared h plus 3xh squared plus h cubed minus x minus h. Then we have minus x cubed minus x. We're dividing that whole thing by h. So this piece right here is just our f of x plus h, and this is our f of x. So now we're going to cancel off like terms. So the limit as h goes to 0, and canceling things off, we're left with, we've got an x cubed here minus x cubed here. We have a minus x here plus an x here. And so we're left with just 3x squared h plus 3xh squared plus h cubed minus h, all divided by h. Now notice there's an h on everything in the top, so we can factor that out. To have h times 3x squared plus 3xh plus h squared minus 1, all divided by h. The h's cancel, and we're left with the limit as h goes to 0 of 3x squared plus 3xh plus h squared minus 0, or minus 1, which then equals 3x squared minus 1. And so that then is our derivative. The derivative of f is 3x squared minus 1. Now just to reiterate what this is a function that tells us the value of the derivative of f at any given point. And so if we wanted to find the line tangent to y equals x cubed minus x at the point 2, 6, so if we wanted to find the line tangent to this curve now, rather than having to actually look at a limit again, we can just plug 2 directly into f prime to get the slope. So f prime of 2 is going to be 3 times 2 squared minus 1, which is equal to 12 minus 1, which is 11. And so the slope of the tangent line is 11, and we've got the point 2, 6. So we have y minus 6 equals m times x minus 2. So y minus 6 equals 11x minus 22. Moving things over, we have y equals 11x minus 16. And so this then is our tangent line to the curve at the point 2, 6. And so by finding this derivative formula, we were able to find the tangent line very quickly. And we could do this for any point on the curve y equals x cubed minus x, rather than just having to do it point by point. We now have a formula for the slope. So let's look at another example. So next we want to find the derivative of y equals the square root of x. And so here, if f of x equals the square root of x, then f prime of x is going to be the limit as h goes to 0 of the square root of f of x plus h minus f of x, all divided by h, which is the limit as h goes to 0 of the square root of x plus h minus the square root of x, all divided by h. So now we want to compute this limit. And so we've talked about how to compute limits like this before. Remember that the trick is we're going to multiply by the conjugate on the top and the bottom. So we're going to multiply by the conjugate of the numerator. So we're going to multiply by the square root of x plus h plus the square root of x on the top and the bottom. And so this becomes the limit as h goes to 0. In the top, we're going to have x plus h minus x. And in the bottom, we're going to have h times the square root of x plus h plus the square root of x. So this is how it simplifies down. We've done this computation with multiplying by the conjugate a few times, so I'm just kind of skipping through the simplification. So now we have the limit as h goes to 0 of just h divided by h times the square root of x plus h plus the square root of x. Notice that we can cancel our h's off. And so we're left with the limit as h goes to 0 of just 1 over the square root of x plus h plus the square root of x. Now we can plug h into the limit, so this becomes 1 over the square root of x plus 0 plus the square root of 0, which is 1, not the square root of 0. This would be the square root of x. So we get 1 over 2 square roots of x. And so this then is the derivative of the square root of x. Now one thing to note here is the domain of f prime is smaller than the domain of f. And so the domain of f of x equals the square root of x is 0 to infinity, including 0. But notice for f prime, that's not quite the case. We can't have 0 plugged in because we'd be dividing by 0. So the domain of f prime of x, which is 1 over 2 square roots of x, is 0 to infinity, excluding 0. And so we got a smaller domain when we did this. And so the domain does potentially shrink in this computation. Now there are a few different notations for the derivative. So just so you're aware of common notations, if y equals f of x, the following are common notations for the derivative. And so we have the one we've been using, which is f prime of x. You can also write it as y prime. We can write dy over dx. We can write d over dx of f of x. We can also write d f of x and d capital D sub x f of x. Now, all of these are notations for the same thing. And so depending on where you are looking in the realm of mathematics and the sciences, these formulas can show up in various places. Within these lectures, we will exclusively use the first 4. We won't really use the last 2, but the last 2 do show up sometimes. We're just not going to use them in this course. And so one thing that can be slightly helpful to be aware of is the notation d over dx is called an operator. And so this is kind of like if we write something like a plus in the middle, it's saying do the operation of the derivative. And so when we write d over dx of something like x cubed minus x, we computed this earlier. This was 3x squared minus 1. That was one of the ones we did a minute ago. Now this notation of d over dx is saying find the derivative of x cubed minus x. Well, if we write dy over dx, we would just write this as 3x squared minus 1. And so this is a very subtle thing, but this is saying do the derivative where this actually is the derivative. And so it is slightly different. We will use the d over dx notation to kind of shorthand saying find the derivative of the following. And so it is very subtle, like I said, but it's just something to be aware of. So now let's look at one more example. So given y equals 3 plus x over x minus 1, we want to find dy over dx. Which again, all that we're asking for here is we're asking for the derivative. So now with this one, we are going to do things slightly different than what we did before. So there are 2 definitions of the derivative, so we're going to use the other definition now. So we're going to take the limit as x approaches a of this function 3 plus x over x minus 1 minus 3 plus a over a minus 1 divided by x minus a. So this is using the other definition. Now technically the final answer is going to be in terms of a, not x with this definition. So we'll just change the final answer to have x's instead of a's. And you'll see that when we get there. But we can use this definition just as well. And so now what we want to do is we want to compute this limit. So we're going to get a common denominator in the numerator to start with. So we have the limit as x goes to a of 3 plus x times a minus 1 over x minus 1 times a minus 1 minus 3 plus a times x minus 1 divided by x minus 1 times a minus 1, all divided by x minus a. So we're just cross-multiplying to get a common denominator. So the limit as x goes to a. Multiplying out the top, we're going to have 3a minus 3 plus x times a minus x minus 3x minus 3 plus ax minus a divided by x minus 1 times a minus 1, all divided by x minus a. So we want to simplify things out. And so we have here the limit as x goes to a of 3a minus 3 plus xa minus x minus 3x plus 3 minus ax plus a divided by x minus 1 times a minus 1 times x minus a. So remember this whole multiplying by the reciprocal trick that we've used before. So now we want to see what things cancel. So we have a plus 3 here and a minus 3 here. And then we have a plus xa here and a minus xa there. And so overall, we are left with then, if we simplify this, if the limit is x goes to a, on the top we're left with a 3a plus an a, so we're going to have 4a minus 4x. Then on the bottom we have x minus 1 times a minus 1 times x minus a. So now notice I can factor a negative 4 out on the top. So factoring a negative 4 out, we are going to have negative 4 times x minus a. And I picked negative 4 because I wanted x minus a to show up. We've got x minus 1 times a minus 1 times x minus a. X minus a on the top and the bottom cancels. And we're left with the limit as x goes to a of negative 4 over x minus 1 times a minus 1. And now we can just plug a directly in to get negative 4 over a minus 1 times a minus 1. So we get negative 4 over a minus 1 squared. Now remember I said we'd end would be in terms of a, but we kind of want it to be in terms of x. So we're just going to replace a with x. So dy over dx is negative 4 over x minus 1 squared. And so that then is the derivative of our function in this case. And so remember that this is a function that tells us basically what the tangent line slope is at any given point in the domain. And so just like we had the idea of being continuous at a point, we're now going to define what it means to have a derivative at a point. And so a function f is differentiable at a if f prime of a exists. It is differentiable on an interval a comma b if it is differentiable at every number in the interval a comma b. So basically you're differentiable if the derivative actually exists at those points. So this is a lot like the idea of being continuous at a point, or continuous on an interval. The only difference here is we're only defining it on a open interval, rather than a closed interval because we don't really have a way of doing one-sided derivatives. We could define a one-sided derivative, but our definition doesn't allow for it, so we just define it not to happen at the endpoints. So now we want to look at an example of a function and where it is differentiable. And so we want to find where the function f of x equals the absolute value of x is differentiable. So this is asking where does f prime of x exist, so let's actually compute f prime of x. So we're going to do it in two parts, so remember the absolute value of x is equal to x if x is greater than or equal to 0, and negative x if x is less than 0. And so we're going to split it into parts. And so part 1, we're going to assume that x is greater than 0. And so if we choose x to be greater than 0, then f prime of x is the limit as h goes to 0 of the absolute value of x plus h minus the absolute value of x divided by h. And now picking h small enough, we're taking limit as h goes to 0, so h can be as small as we want. Picking h small enough, we can assume that x plus h is greater than 0. Even if we're adding on a negative h, just make it small enough that the x plus h is still greater than 0. And so because of that, this is the limit as h goes to 0 of just x plus h minus x divided by h. Just the limit as h goes to 0 of h over h, which is 1. And so if x is greater than 0, we get a value of 1. And now if x is less than 0, we're going to do something similar. So we have the limit as h goes to 0 of the absolute value of x plus h minus the absolute value of x divided by h. So now in this case, if we pick h to be small enough, we can assume x plus h is less than 0. X is a negative number, and we're just going to plug in a really small h to make sure we stay negative when we do x plus h. And so because of that, this becomes the limit as h goes to 0 of negative x plus h minus negative x, all divided by h. And this just follows from the absolute value, how it's defined. Since we're assuming x plus h is negative, the absolute value of x plus h is negative x plus h. So now simplifying this, we have the limit as h goes to 0 of negative x minus h plus x divided by h. Just the limit as h goes to 0 of negative h over h, which is negative 1. And so we see here what the derivative is when we're greater than 0 and when we're less than 0. So now we're going to consider what about when we're at 0. So now when x equals 0. So we have the limit as h goes to 0. Now we're going to do it from the right and from the left because it's going to depend on if h is positive or negative. And so to see that, this would be just f of x plus h, but x is 0, so we're going to have 0 plus h minus f of 0 divided by h, which is the limit as h goes to 0 from the right of the absolute value of h minus 0 divided by h. So we have the limit as h goes to 0 from the right of the absolute value of h divided by h. And now this is why it's important that we're going from the right or the left, because the absolute value of h will depend on if we're going from the right or from the left. And so we're going from the right here, and so this is just the limit as h goes to 0 from the right of h over h, which is 1. But if we changed and went from the left, we'd have the limit as h goes to 0 from the left. All of the math works out the same, so we have the absolute value of h over h. But now, because we're going from the left, h is a negative number, so this becomes the limit as h goes 0 from the left of negative h over h, which is negative 1. And so notice, these limits don't agree. We get 1 from the right and negative 1 from the left, and so because of that, the limit does not exist. So the limit as h goes to 0 of f of 0 plus h minus f of 0 over h does not exist. So in other words, f prime of 0 does not exist. And so then what we have is that the function f of x equals the absolute value of x is differentiable on the interval negative infinity to 0, union 0 to infinity. And the derivative is defined to be 1 if x is greater than 0, and negative 1 if x is less than 0. And so that then is our derivative. And so we see that this point of 0 became a problem. And so we want to talk about what things can we kind of look out for to tell us if we're going to be differentiable somewhere or not. And so to do that, we're first going to mention a theorem. This will just kind of speed up one of the things we're going to look at graphically. And so we have the following theorem. If f is differentiable at a, then f is differentiable, then f is continuous at a. So if you're differentiable at a point, then you are continuous at that point. This just comes from the fact that if we know the derivative exists, if f prime of a exists, we know that limit exists, and manipulating it, you can show that the limit as x approaches a of f of x must be f of a. So you'll have to be continuous there. And we're just mentioning that so when we look graphically at what things can go wrong, we can kind of simplify the situation a bit. So there are three situations in which graphically a derivative won't exist. And so the first one is just corresponding to what we just said. If f is not continuous at a, then f is not differentiable at a. So if you have a discontinuity, then you're differentiable there. So just going off of an example of one discontinuity, we could have something like this. If this is our point A, we would not be differentiable at A because we're not continuous there. Now, it doesn't have to be a jump discontinuity. It could be a removable discontinuity or an infinite discontinuity as well. So that's the first way that things can break. The second way is what happens in the absolute value of x. So if we graph the absolute value of x, its graph looks like the following. And so this is y equals the absolute value of x. And notice what's happening at 0. At 0, we changed directions very abruptly. So we had a slope of negative 1, and then we had a slope of 1. We changed slopes very abruptly. And so this is what is called a corner. Now, it could happen in another way. We could have the following situation, where instead of changing necessarily abruptly, it might just become, still changes abruptly, but it goes off to infinity. This is what is called a cusp. And so these are two ways in which the derivative also might not exist graphically. So if you have a corner or a cusp, which is just saying that you change derivatives very abruptly. And so these are two ways where graphically you might fail to have a derivative. And to see in the second one, if you just look at tangent lines, notice our tangent lines essentially become straight vertical lines as we get closer and closer to our cusp. And so we'll fail to have a derivative at that point. And so that's graphically the second place what can happen is if you were at a corner or a cusp. Now the third way that it could fail is what we call an infinite tangent line. So the third possibility is an infinite tangent line. Now this sort of aligns with what happens with a cusp, but we treat it a little bit differently because cusps are a bit unique in what's happening there. In this situation, the limit won't exist. So in this case, if you looked at the limit as x approaches a, if this is the point a, of f of x plus, I guess I'm doing the other definition, f of x minus f of a over x minus a, in both of these cases, this is not going to exist. But in the next case, it actually does exist. Well, it doesn't exist, but we can give a number for it. And so in the case of an infinite tangent line, what happens is the limit as x approaches a of f of x minus f of a over x minus a is equal to plus or minus infinity. Now, technically that means the limit still doesn't exist, but it doesn't exist in a special way. And so it's a little bit different of a situation. And so graphically what happens here is it looks something like the following. These ones are a bit harder to draw, but what happens is it becomes completely vertical at some point. And so at some point here, the tangent line is perfectly vertical. Now it looks like it's perfectly vertical for a lot more than just that point A, because I'm a bad artist. But you get this point where you become perfectly vertical, and that then is a way you can fail to have a derivative there, so you're not differentiable. So kind of an easy way to think about it graphically is that if we zoom in on the point A in the graph of y equals f of x, and we have a non-vertical line when zooming in, then f is differentiable at a. So remember we talked about this idea of tangent lines, that if you zoom in on the point really, really close, the graph and the tangent line become indistinguishable from each other. So that's the idea here, is if you zoom in on the graph really close at that point, you're essentially looking at the tangent line, and if you have a non-vertical line, then the function's differentiable at f. So that's one way of thinking about this.